Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection, of course. Today is the so-called Pea-and-sun paradox, or how I like to call it. I stole this idea from a certain book, which is called the Pea-and-sun paradox, linked in the description, which is really amazing. I would like you to have a look at it. As I said, all of the video is motivated by this book, basically. Another name for this theorem paradox, which is probably more familiar or more popular, is the Banach-Tarski paradox, which is really a classical and popular topic in mathematics, linked to a few videos and documents in the description. So it's really, really popular. And because there are so many videos and links and descriptions and pictures and whatever, I like to give you a slightly different point of view. In particular, I would like to explain the proof sketched in, or really given actually in this book, The Pea-and-sun paradox. It's a really nice book, and it's self-contained and gives you the proof of this very surprising theorem. Okay, by the way, I will tell you in a second why I call it theorem and not paradox, but the classical name is paradox anyway. And it's a very surprising statement, and I learned it in the following formulation, that one orange equals two oranges, which is the starting point for this video. So here we go. The paradox, in quotation marks, is the following. So if you have an orange, then you can rearrange it in certain finite number of pieces and piece them together again and get two oranges, right? You have one orange, you cut it apart into finite number of pieces, piece them together again, you get two oranges. That's a paradox in the sense that it's surprising. So paradox is usually an umbrella term. It could mean many things. In this case, as I said, it means more like surprising, counterintuitive, instead of the maybe more familiar it leads to a contradiction. This doesn't lead to a contradiction. It's surprising. It's a theorem, not a paradox. Anyway, this is how I learned it. So I think it was my first class on analysis a long time ago when I was young. Yes, I was young at one point. And the lecturer of this class took out an orange and said, yeah, I show you today a way to take this orange and create two oranges. Took out a second orange at the same time while saying this. I actually wanted to do the same trick, but I decided that's probably a waste because I don't like oranges. I would just buy them and throw them away. So I decided to just go with a picture because all of you know how an orange looks like anyway. Wherefore, let's come back to the paradox. So you can take this orange, you decompose it, and you get two oranges. And that's already very surprising. Even more surprising is that you can do it in, well, a finite number of pieces. You can do it as, well, 5 pieces suffice. The proof I'm going to show you needs a few more pieces, so not the 5-piece proof. You can count how many pieces I need. It won't be 5. And anyway, I won't need much more pieces than 5 anyway. And that's very surprising. So you can decompose your orange into a certain number of pieces, and you can rearrange them again. Before you start doing that, so running around trying to buy oranges and try to get 2 oranges out of one, because you think, okay, if I get 2 oranges out of one, I also get 3 oranges out of one, and I also get 4 oranges out of one. I also get 5 million oranges out of one. Yes, in the theorem that works, of course, but in practice it doesn't really work because, as I'm going to explain, this needs a certain axiom, which some people don't like. So there's some philosophical questions around this axiom, which is called the axiom of choice. We go there later. So the problem is that those 5 or 6 or 7 or 8 pieces, whatever, this finite number of pieces, they are not pieces in the sense of, well, little pieces like whatever you can cut out of an orange. We will see. Actually, I'm a little bit doubting that you can do this trick in real world anyway, because, well, I'm not a physicist, I don't know. But some people would say that the world is quantized, so you have kind of a minimal particle. And as you will see, this really needs the real numbers in the sense that they're kind of very, very dense, right? So they're very, very clustered together. Anyway, so maybe what I said is maybe my analogy with oranges is not really perfect. This is a mathematical theorem, right? It might not work in practice. And it's even more paradoxical than you think because, well, the pieces themselves, they are crazy. But the operations you do on the pieces are rotations. So everything is built from rotations, as I'm going to show you now, because now I'm kind of trying to give you an idea how to prove it, and without giving you all details, of course, because this is still a YouTube video. All the details are in the self-contained book. It's really, really self-contained. You can read it as a high school student in mathematics. Well, as a high school student or as an undergraduate student in mathematics. It shouldn't be a big problem. It's really self-contained. It goes through all the details. Really, I would like you to have a look. It's really nice. Anyway, roughly the proof goes as follows. So kind of what you should keep in mind is that R3 is pretty crazy and rotations in R3 are even crazier. So the first thing you might ask about the theorem after we have all relaxed and accept that this is very surprising is why do I show you this theorem with oranges and not with, let's say, circles? It would be easier to illustrate circles and not oranges, right? Something in 2 dimensions. This doesn't work in 2 dimensions. You really need a 3 space because, well, strictly speaking, I show you a way that involves, show you a way to prove it that involves 3-dimensional rotation. So strictly speaking, I don't know whether you can get away without using rotations. Anyway, that was just waffle anyway, so you can ignore it. So let's have a look at mathematics. So I would like to consider my sphere, my little ball here, and I take 2 rotations in 3 space, which of course fixes sphere, they just rotate it in some way. I take this rotation tau, which goes all the way through the z-axis, so it's a bottom to top axis, and is rotation by 120 degrees. So 120 is a third of 160, 360, so this cubes to 1. Right, you can do it 3 times and you're back to where you started. That's my first rotation, tau. I have a second rotation, sigma, which is along this 45-degree angle here, which is roughly the, which is not roughly, which is the axis x equals z. So it's roughly if you know how the Earth rotates around its own axis, the axis of the Earth is a little bit tilted. It's roughly the same. So you're a little bit tilted towards the bottom and top, and now you rotate by 180 degrees. In particular, sigma squared equals 1 because of a rotation by 180 degrees. Right, very good. So this axis roughly comes out here somewhere, and then that's your rotation axis. You take those 2 elements, so those 2 rotations, and compositions of rotations are rotations. So they form what mathematicians call it a group, which I call G. And the first surprising fact about G is that G is actually an infinite group. And this is already kind of suspicious. Infinite things in mathematics are always a little bit suspicious. And this will be kind of the point to build everything. So you need this infinite group, which basically is a free group. If you know what a free group is, this is basically a free group in 2 generators. But we don't need to know that. We only need to know that there are certain very, very explicit rotations of my sphere. And everything on this slide is still very explicit, everything. Also, I don't write it down explicitly, or I don't give you the algorithm, but everything on this slide is given by an algorithm, basically. In particular, this decomposition of G, of my group, of my rotations, into certain subrotations. The combinatorics of those subrotations are important to get the result on the next slide, but I won't go into details. It's a little bit painful to write it down. It's not bad, it's an algorithm, but a bit painful. I don't want to do it. The only thing you need to know is there are 3 infinite sets, partitioning G, G1, G2, G3, and there are certain of those rotations just put together in one box. And the next thing you do, there comes the set P, which you take out. It's not so important, but it fits on the slide. So every rotation, of course, has a rotation axis. So if you stick your axis through S2, so this is my sphere here, S2, if you stick your axis through, then you have 2 points on the sphere which are fixed by a rotation. So for my tau, for example, it would be the north and the south pole. For my sigma, it's a point down here and the point here. And you take all of these points for all of these infinite elements, you take them, collect them in a set, and I call it the set of poles because it's really this generalization of the north and the south pole for tau. So collect all those rotation axis points for all of those rotations. Collect them in a set P. Up to this point, everything is explicit. I could, in principle, write down all rotations. I could write down the sets G1, G2, G3, And of course, I already written down the set as a group G anyway. So everything very explicit, just rotations in 3 space, certain rotations in 3 space. Okay, and now comes that thing which is not explicit anymore. That's why you can't do it in practice. I will come back to that later. So enter our funny axiom of choice. So what is the axiom of choice? Well, I won't give you the formal definition. It's a bit painful to write it down. It's not too bad, but it's a bit painful. But basically, the main idea is as follows. So mathematicians would like to build mathematics itself on some solid ground. And the solid ground itself should be just given by here are a certain number of axioms, so which are unprovable things that you assume to be true. And now we build mathematics from there. And a very popular strategy or a very popular set of axioms is the Zermelo-Fraenkel set theory. There's certain axioms underlying set theory, unprovable things. Here's an example which is almost, well, like if you have a set theory, you don't want to talk about something empty. So one of the axioms basically says there is a set, right? You're not talking about something empty. And yeah, sure, this will be unprovable in the theory itself because you might end up talking about something empty. Yeah, but it sounds reasonable. Other axioms in this setup of set theory are a little bit like if you have a set A and you have a set B, then A union B is also a set. It's like a Lego principle. So all of them are very believable. Some people might argue that there is this axiom of infinity, which they would kick out. But anyway, so most of them are pretty believable and easy to write down and whatever. So most people would accept those axioms. And then there comes this axiom of choice, which is a bit painful to write down, just super useful in practice. So most people would accept that as well. But it leads to some funny things like the Banach-Tarski theorem. What it roughly says is that whatever kind of set you have, and sets can get pretty crazy, you can always choose elements from your sets. And that's what I'm going to do in a second. If you don't like that informal definition, let me tell you my two favorite equivalent axioms, so equivalent statements, which you could use as a substitute for the axiom of choice here. They're not related to choice in some sense anymore, but they're equivalent. So one of these equivalent statements sounds very harmless. You have a set A, you have a set B, and then you have a surjection either from A to B or from B to A. So one of them is bigger in some way. It surjects to the other. Sounds pretty harmless. Here's my favorite one, again, equivalent to the axiom of choice. Every vector space has a basis, equivalent to the axiom of choice. In some sense, what you do is you choose a basis for your vector space. Axiom of choice is this slightly weirdish axiom, which has a slightly complicated formulation. It has very harmless sounding equivalent properties. It has very strong sounding equivalent properties. For example, the well-ordered theorem. Every set has an order comparable to the order on the natural numbers. And there are some really weird statements equivalent, like Zorn's lemma. I don't even want to spell it out. It's a little bit weirdish. So it's a little bit weirdish, and it leads to some funny contradictions in mathematics. They're not really contradictions. They're just really strange. And one of them is this Banach-Tarski paradox, what we are discussing right now in this video. Anyway, keep in mind the axiom of choice is a certain choice of axiom. Sounds funny, but anyway, it is a certain choice of axiom not everyone would agree with. I would say most people would agree with it, but not everyone would agree with it. I certainly like it because I like the statement every vector space is the basis, but some people wouldn't. So in some sense, this step here is this implicit step. This is not explicit anymore. And this is the one you can't do in practice. And maybe that's why some people don't want to do it. Some links are in the description if you want to know more from that perspective. If you're a constructive mathematician, for example, you only want to have statements in mathematics which are constructive in nature, that you can really do something by an algorithm, for example. This is not one of them. Anyway, this was a long waffle about the axiom of choice. Let's take it for granted for today. Then you partition, so back to our problem. So partition your set S2 into P, S2 without P. So you take out the sets, those pole points. As a reminder, because my waffle was so long, those pole points were those guys here. So the north and the south pole, and the other 2 points plus infinitely many others coming for all the other poles of the group elements. And you use this, you use the group now, and it gives you orbits because it acts on those points, so it gives you a lot of orbits. And from each of those orbits, which are these uncountable sets, these huge sets, you obtain a certain set by picking, that's where the axiom of choice comes, you pick out one element per orbit, and you get a set C. This set is, there's no way you write down this set in a sense that I'm going to explain in a second. This set is extremely unexplicit. If you accept the existence of the set, the rest is explicit again. So let's go to the rest, and where the paradox kicks in for the first time, given by the Hausdorff partition. So what is the Hausdorff partition? Well, you can now create sets K1, K2, and K3 out of C and G, the corresponding G1, G2, G3 from the other slide. And remember, those were completely explicit. And you get a partition of your, so these are disjoint unions of your S2 without P. Okay, you have partition. That's nothing interesting. You have partition. Okay, yeah, sure. But the partition satisfies a really weird property. That's why it's also called the Hausdorff paradox, or instead of the Hausdorff partition. Namely, all of those sets are congruent. So K1 is congruent to K2, is congruent to K3. So here's my picture. So I take this funny S minus P, or S minus P is just the same notation for S without P. I stole this picture from the book. That's why the book has a slightly different notation than I do. So S minus P is S Z minus P. Anyway, you partition it in your three sets, K1, K2, K3, and I illustrate. In this illustration, they are of the same size, and that's exactly what they are, because they are all congruent to one another. They're kind of, you can't distinguish them in some sense. So all of them are a third of my sphere, right? I've partitioned it into equally big parts, K1 and K2. And now comes the Hausdorff partition. Now comes Hausdorff and tells you, well, all of them are actually also congruent to K1 union K2. And now we are in trouble in some sense, because if K2 is a third and K3 is a third, what is then K2 union K3? It should be 2/3. But on the same hand, it's still congruent to K2, so it's still 1/3. So we are in trouble. 1/3 equals 2/3. So we are in trouble, or whatever we want to call it, because now we can play the following game. Okay, K1 is congruent to the union. So just split it into the union. K2, split it into the union. K3, split it into the union. And now you have 6 pieces, all of which are congruent to the 3 pieces, and which still gives you a decomposition of this S2 without P. Okay, this is weird. So let's, and you're done basically now, because now we have, I mean, you can play this game now forever, right? So this is bad in some sense. So as I just said, this one is 1, 2, 3. And here I created 2, 2, 2, and 3, 3, 3. So the only thing you need to do now is you need to say, okay, we also know that K1 was the same as K2. So you can change one of them to 1. You also know that K3 is the same as 1. So you can change one of them to 1. And you get another 1, 2, 3, 1, 2, 3, and another 1, 2, 3 copy. So you just have obtained 2 copies of the same thing, right? So we are there, right? We have decomposed S2 without P into 2 copies, which are completely equal. Very surprising Hausdorff paradox. And it really comes from this, we have these 1/3 pieces, and the union of 2 1/3 pieces is still a 1/3 piece. That's just bad. If you just think about the calculation you would like to do here in numbers, that's just a bad calculation. You shouldn't do that. Something will go wrong, right? And you split everything, and everything should get smaller, but it doesn't. It just kind of stays of the same size. And yeah, we're basically done. So the last step here is not very exciting anymore. You might say, well, you have S2 without P. That's not really S2, and it's also not really the orange, it's not really the ball. But you can thicken up everything. So basically from S2 to the ball is not hard anymore, and the set P doesn't really play a role anyway, because for the experts, it's countable compared to S2, which is uncountable. You should thicken it away and it's gone. You can ignore it. So basically, this was the proof. And the only non-explicit ingredient was this set C obtained from the axiom of choice. Yeah, and that's then the Banach-Tarski theorem formulated now with balls instead of oranges, because it's a mathematical statement. And really this trick of constructing the set C, I don't see this happening in practice, so you shouldn't go to the next grocery store and buy oranges. Probably you can't do that. I haven't checked myself. As I said, I don't buy oranges, but you probably can't do that. And the point is, I showed you a proof involving axiom of choice, right? The construction of the set C. It doesn't mean you can't do better. Maybe you're much smarter than me and much smarter than the author of this book, where I stole the idea from, and you can just find a way without the axiom of choice. You actually can prove that you can't. So this statement is not provable in Zermelo-Fraenkel without choice. Then you might argue maybe Zermelo-Fraenkel is not the right thing, the right foundations for mathematics anyway. You might want to take a more modern approach using categories or whatever. That doesn't matter for this video, but in Zermelo-Fraenkel, this statement can't be proven without choice. Right? You might write down a different proof. In particular, my proof didn't give you 5 pieces, but a few more, as you probably have observed. And so that's a proof with 5 pieces, linked in the description. And yeah, well, but you still would need some version of axiom of choice. It might come in disguise because it has so many equivalent forms, but you still need some version. And of course, you can also then push it further. This is not quite trivial. I mean, if you can decompose an orange to 2 oranges, sure, you can play this game and you can decompose it into 5 million oranges, but you can also get infinitely many copies at once, which is an extension, an honest extension. It's not completely obvious, but it's maybe not surprising anymore if you already know the original statement. What I would rather like to go into is into this picture here. So this is a picture of cosmic microwave background of the universe. And this is really how I would like to think about the sets K1, K2, K3. They're not nice pieces that you can stick together. They're really like this cloud-like things like on this picture. So K1 is this red, yellowish thing, and K3 is a green thing, and K2 is a blue thing, and they're kind of cloudy-ish pieced together, and it's not quite clear where they intersect, where they don't intersect, but how they interlace. And this is how you should think about those sets K1, and K1, K2, and K3. And that's also the reason probably why you can't. I mean, you probably can't do this with an orange, right? But anyway, I really like this analogy of cosmic microwave background and those sets turning up in the decomposition of the Banach-Tarski paradox. Which I stole from one of those articles linked below. It's really a nice analogy that I would like to sell here. Anyway, so I'm basically done, but I haven't told you anything about peace and the sun. So where are the peace and the sun? Well, here's my P, a P on the table. P is very small. And a sun, well, a picture of the sun. Or honestly, I think this is not a real picture of the sun. This is a recolor picture of the sun. I think the sun is so bright, if you would take a picture of it, it would just be a white circle. I'm not a physicist, I'm not sure. Maybe a white circle with some black dots here and there. But anyway, this doesn't really matter. This was Raffle. This doesn't really matter. So this is the sun, and this is a P. One of them is very small, one of them is very big. And turns out that you can use Banach-Tarski to show that they have the same volume. They're the same, they're congruent in some sense, which is really kind of very surprising now. I mean, something very small, something very big should have the same volume. And this really lies at the heart of measure theory. Measure theory is in part of mathematics where people try to come up with a regular theory of areas and volumes. And that's a bit tricky, and there are a lot of that theoretical issues involved. And this is really one of those problems that lies at the heart of measure theory. An even stronger version is written down here below. You might want to call this the mosquito and elephant theorem, because I don't actually need balls. Any reasonable subset of R3 will do. So any reasonable subset of R3 has the same volume as any other reasonable subset of R3, which I think is an extremely surprising statement. It's a paradox in the sense of being a little bit surprising or not quite intuitive. Anyway, I hope you ignored my waffle throughout this talk. I waffled a lot about the axiom of choice and so on. Anyway, so there's this really nice theorem, Pea-and-sun theorem, saying that the P and the sun are basically the same, and I like it very much. It's at the heart of set theory, at the heart of measures theory. It's very surprising. It's paradox in the sense of being surprising, not in this. I say it again, not in the sense of there's a contradiction. There's no contradiction anywhere. As soon as you accept axiom of choice, you basically go get there, and that's a real theorem. And I like it so much because of this analogy with the P and the sun, which is really cool. And also the picture with the cosmic microwave background for me was really nice when I learned about it. Link to the articles as I said in the description. Anyway, I hope you enjoyed the video, and I also hope to see you next time.